Okay, thank you so much, and Sean for organizing this, and Adej for all the work here. And so I come a little bit from a different place. I'm right in the heart of the math world over here, but in some sense you can think about this generally at the UW as being a talent pool that is very interested in what AI medicine is interested in, and it's a great group of students broadly across the University of Washington in computer science, applied math, statistics, all who want to do something meaningful in their research. And it starts kind of with data. I think one of the most exciting parts about the current world that we're in is that it's become absolutely clear that you can't work by yourself. If you want to do good work, it's not like you can say, I can understand the entire problem. I'm an expert in machine learning all the way to some area of medicine. I think it's becoming uncomfortable for us to say, I have my expertise, let me work with others with great expertise. And I think that's part of our philosophy here is to try to produce students, postdocs, who have great skill set, who want to make impact, and who can partner with people like yourselves to do transformative work. So the Institute's on dynamic systems. So let me first talk about this from the perspective of who's involved. We actually built this very much out of the UW Medicine's WWAMI model, right? So we brought in a Pacific Northwest strength. We are partnering with, it's led out of here at the University of Washington, but we have Montana State involved, Portland State is involved, Boise State, Nevada, Alaska, Hawaii. So that's our sort of, let's say, a Northwest hub of strength, and we're bringing in a lot of different people there. And it's this very interesting culture right now where a lot of the machine learning talent has focused in on a few cities in the United States. This is where our big companies are: Seattle, San Francisco, Boston. So for instance, imagine trying to hire all these top-end machine learning talent, let's say, in Bozeman. It's a hard thing, right, when we look at the pay structure of what's happened. And so what's happening with us is being able to essentially spread that knowledge out across these institutes. And we've also brought in our East Coast partners, Harvard and Columbia. And you can see some of our strengths are around these little boxes and colors here, which is we have a lot of dynamic modeling. And so many, if you want to think about it, you can think about biophysics modeling. We want to think about things evolving in time, which is oftentimes when we take snapshots of a data, it's static, but really if we start looking deeper, things are progressing over time, and that's what we're really interested in building models for. We have great expertise in optimization, statistics, control theory, as well as physics-informed machine learning, or you might want to think about it and twist it to your framing as biophysics-informed machine learning. How can we capitalize on all the know-how that you guys have to build models that are a little bit more directed at the application that you guys have in mind? So this is the team, and it's a great team, very collaborative. It's got a great culture, and we want to do really interesting problems. And so again, if you guys have interesting data sets, that's where the collaboration can really happen, is if you've got the data sets, we can come in and sort of, I don't think a few of us know biology. I don't. But I work with neuroscientists, and that works out well because I let them just know the neuroscience, and I just help out with my math when I can. So let's talk about what we're after. And I'm going to give it as in terms of a historical story here. This is the night sky. And what you're looking at here in the foreground is the trajectory of the planet Mars collected over a very long period of time. And this is the retrograde motion in the sky of what the planet Mars was doing. And here, over here, is the planet Saturn. And in some sense, this was science, right? This is what everybody looked at in the night sky. People wanted to understand the trajectory of planets. And so in some sense, we get right to the idea of like discovery and how we want to start modeling things. So certainly biology and medicine is at that phase where the data we're collecting now are allowing us to say, can I produce mechanistic models that are generating what I'm actually seeing, right? So I think one of the stars of all the shows that we're looking at are sensors. You know, we talk about machine learning all the time, but to me, the star of this century is sensor technology. I can't believe what you guys can actually collect data-wise. And so with that data, how do we start building models that are informative and start getting us to a place where we can do quite a bit with things? And here, at least, you could just look up at the night sky back in those days and measure these locations of planets. Okay, there was no light pollution. You can't do that today in Seattle, but back then, you could do that. Go outside. Okay. So let's talk about the evolution of ideas here. And this becomes important because even though this is a very simple story, it's reflected in our modern-day machine learning. So we came up with models. And the first successful model, came out of Alexandria, Egypt, 150 AD approximately. It was known as the doctrine of the perfect circle. And the way that the model came out was Claudius Ptolemy. Alexandria, by the way, is a fascinating city. It's one of the most fascinating cities in all of history. So out of this, you come and you have this development here. We have geometry is developed there with Euclid. You have algebra developed there. Most high school kids would probably hate this place because geometry and algebra both came out of this city. So it's like, knock that off the list. But really a fascinating place in terms of math development, science development, and actually even medicine with Galen having spent most of the formative years of his career there because the Egyptians, in fact, right, with their mummification technologies, Galen was then able to take that and then use that in Rome and build out sort of medicine from there. But 150 AD, here is the model of planetary motion. This is the idea of circles moving on circles. So this was the outline of how we could understand that retrograde motion. And so, you know, here's the picture. Here's the Earth. Here's a planet going around. So it's going on a great circle and smaller circles, and that's how you could see the back and forth motion. Okay? So this is a Earth-centric coordinate system. And part of what we want to do is start thinking about how would we model this in current machine learning technologies. So the first thing that they discovered was a coordinate system. The second thing you discover is then the dynamics in that coordinate system. And much of what we focus on is exactly those concepts. And I think that's extremely important for even modern-day applications in biology is what are the right variables? So when I say the right coordinate system is, I really mean how do you represent this dynamics? What should I be using as the variables to represent this dynamic? And then how do I then represent its evolution? And so this picture up top is sort of our generic picture of what we want to think about, which is we're going to use sort of these neural network architectures, for instance, to learn for us a good coordinate system. I almost said the right coordinate system. I'm going to come back to that in a moment because, in fact, this is quite an accurate approximation. This theory lasted 1,500 years. It was so good that it became dogma, right? And whenever it's dogma, you know there's problems. Okay. But that was model number one. And it had a huge impact scientifically. We finally had a theory to explain what was going on in the heavens. Model 2. Okay, shortly after this, by the way, we go into the Dark Ages. So say goodbye to advanced civilization for a while, and then out of the Dark Ages, we start emerging into the sort of the Renaissance period where Model 2 comes out. And Model 2 is interesting. We start to push this idea, so Copernicus, and actually Copernicus picks up a theory that came out of Alexandria before Claudius Ptolemy, which is, well, things go around the sun. This is an old idea. In fact, it predated Claudius Ptolemy's many hundreds of years. And the idea was what we normally teach in our schools right here, which is the heliocentric universe. The sun is the center, planets go around it. This was a pretty revolutionary idea. So it's a new coordinate system. for us. And in that new coordinate system, 80 years after we have this new coordinate system, Newton comes along and says, hey, by the way, here's the dynamics in that coordinate system. We have F equals ma. So you have to have the right coordinate system to be able to have F equals ma appear for you as the model for this. Now, it took about 100 years, by the way, before this model actually took over, because we'd worked on the Ptolemaic system for so long, it was quite accurate. And so, but then this got adopted. And you could ask the question, if we look at Kepler versus Newton, Kepler had, written down his Keplerian laws about sort of really being able to have a model for this, just having the right coordinate system. And what's the difference between that and F equals ma? And so, in some sense, what we want to talk about here is there's a huge difference of what's going on here. So Kepler, who had, in fact, a heliocentric model that worked quite well, is that Kepler's model was a fit to the data. It was an interpolation. F equals ma is an extrapolation. With F equals ma, you can do the following. I wonder what it would take to launch a rocket, put it around the moon, and come back. That's in nobody's data set. Right? By the way, we're not sure we really quite believe it. That's why we send pigeons first, then monkeys, then a human around just the Earth once. Then you say, okay, maybe this all holds. Now let's send a human to the moon, right? So this is the big deal here. And you can say, well, I'm talking about planetary motion, but it relates directly to what we're seeing as the modern applications today. So robotics, autonomy, and of course, for you guys in medical profession, we're already seeing medical robots. But these are amazing technologies that we see emerging using these concepts. And this is much more maybe closely related to the things we're going to study at the AI Institute for Dynamic Systems, is building great controllers, great models, great sensors for enabling these. But there is a fundamental difference between these two technologies. They're both autonomous, but it goes right back to Newton versus Kepler. The way that robot is being built is through extrapolation engines, F equals ma physics. It has all these physics engines to help drive it, stabilize it, so forth. The car is a bank of sensors. For the most part, no physics. Rules, sensors, and all of this works, especially down here, provided you provide enough data so that anything you see has already been seen, so that you can use it, you live in an interpolatory world. So I don't want to make too much comments about this except to say both these methods are highly successful. And I imagine in medicine, you're going to have both play out. But you have to bring both of this to the table, I think, in the future. So part of what we're developing is technologies around bringing these things together, because what you don't want to have happen is say, hey, I've got this great model, I can do everything, this is all great. My robot should be perfect because, in fact, I have all the data trained correctly. So these are kind of funny to look at, right? Because they make very human mistakes. Okay, these are your, if these were humans, they'd be coming to see you down there, right? Okay, so we can't have this happen, right, at your hospital, right? This is interesting. We have these top-level technology. You get all the training, you have all the right physics, and here is the kind of stuff that goes wrong. Right now, you imagine you're in a medical profession and practice, and you have all this data set. This is what you can't afford your model to be doing, right? These are lawsuits. And so just because we have the AI and ML, there's a lot still we have to sort through. How do we get uncertainty metrics? How certain are you about your model? These are all the kind of things we have to focus in on because we can't afford this. This is all fun and games here because this is, in an enclosed environment. We're learning. Once you make the translation over to real medicine or really trying to get into understanding that data and have to implement that AI in practice, where people are on the other end of that, that's pretty tricky, and there's a lot still that we need to learn there. Final thoughts about what the AI Institute is doing. What we want to do as well is to try to think about taxonomy of deep learning and machine learning algorithms. Everybody's just trying everything, which is fantastic. But at some point, we need to collect this, start understanding, okay, what are the principles that seem to work with this kind of data for these kind of objectives? It's a little bit like thinking about the periodic table here. The periodic table revolutionized science, right? Because it kind of organized all of these chemicals by this electron that was sitting on the outside. And you could see these paradigm shift. Once you get this, you kind of understand a lot about materials and about science. Right now, we don't have that for machine learning. Everybody just tries stuff. Whatever works. How do you know it works? I cross-validated. Which is fine for where we are right now. But we can't stay there. What we need to do is move it towards when you come to a problem, when you state the kind of data you have, the kind of goals you're after, what's the possibilities of what you can measure, say, oh, for that kind of problem, here are the suite of methods that are applicable, right? Instead of like, just try a bunch of stuff and see what works. It's a free-for-all for right now, but it won't be. And that's part of what we're trying to actually do here as well. So anyway, with that said, thank you for your time.